discussion session after the intro session. So you can see the screen.
Yeah.
Fine, okay. So this will be interactive as before. So we'll ask you questions. We'll give you time. Maybe we'll think. We'll have puzzles. So yeah, so we'll start. So we'll just again we'll do some warm up and we'll go infinity and beyond. And the final question: can machines really do everything? If not, can God can? Right. Very interesting questions. Right. So first of all, the angry atheist problem. So you are a logical mathematician who does not believe in God or the fact that there exists any being that can grant unconditional wishes. So you don't just believe. And suddenly a creature popped up and it said, I'll grant you a wish and that will come true no matter what. And you're surprised. What will you do? So anyone, so I'll just ask, okay, what will you do if this happens?
May I answer?
What?
Can I answer?
Yeah, sure.
So I would like to make a wish and say him that give all his powers to me.
Okay. Okay. That is fine. And I mean, yeah, that is fine. But the point is, you don't really like God. What?
P
What?
versus NP problem.
What?
No, I
It
mean to say
solves.
that if he really has some powers, then I would be agreeing that God really exists. And if he fails to give me his powers, then uh, of course he is not a God.
Can I answer?
Well, if he did give you his powers, then and it proves that there is God, and you're not satisfied, right? You're more sad that, oh man, there is a God, and what you believed is wrong. You you basically want to disprove his existence or something like that.
Well, I would.
Uh,
Okay, so this entity that has popped up is not saying itself to be God, right?
Madhu, you went out of screen share, like not screen sharing. I mean slideshow mode. Yeah.
Yes. Yeah. So someone told something I didn't hear.
Yeah. So
can I
basically,
say
I said
something?
that the
so
entity
bas-
that.
so let me rephrase what Madhu was asking. So basically, this guy wants to show that God cannot fulfill each and every wish. So try to make a wish which cannot be fulfilled by the God. So try to make such a wish. That should be
Yes.
your aim.
Exactly. So given this scenario happens, you have to make a clever wish so that it kind of embarrasses the creature. Like
Okay,
it
so
becomes
he'll try.
helpless. It
I'll
cannot
ask.
I will.
really.
Create a rock which no one can lift.
I will ask him
Well,
to believe. I will ask him to
hello.
believe that he cannot grant unconditional wishes to anyone.
Well, he'll start believing, but still he can. It's just about he's believing that he cannot grant. So, oh, yeah, some people are close, kind of. Someone told create a rock that you
I
cannot
would
lift, but
It was
I
actually
would
me.
ask him to stop existing.
What about square root of -1?
yeah, he will tell it's I.
No, I mean something not like not something humans assume, something proper.
What do you mean? Humans assume that square root of -1 is I. So
That's
do we
what
think?
Euler did. That's what Euler did, right? He couldn't get it, so he's like, it's I. That's it.
No. It's not actually that way. It's kind of those numbers kind of exist, but they show up in
I
different
can
ways.
ask him to.
Yeah, ask him to.
Okay, I'll ask him to make me believe that God
My
exists.
wish would be to,
Hello?
Yeah,
Yeah.
hello.
Yeah, I will
I will
ask
ask
him to
him
make me
to.
believe in God. In that way, I'll win in both conditions. If he doesn't do that, then God doesn't exist. And if he does that, then I'll also start believing in God. So I won't be angry.
Well,
No, your
I
aim,
really
your,
wouldn't
your
like.
aim,
Yeah, fine.
yeah, your
I
aim
will.
should be to ask such a wish which God cannot fulfill. That should be
See,
your
I
aim.
will ask him.
yeah, you don't want to
I will ask.
compromise here. You want to defeat God, basically.
I will ask him to tell me the
I would
largest
wish
natural number.
to that God.
Hello. I will ask him to
Hello.
make me most the cleverest person.
Okay,
Yeah, he
that's
can make
still
you, but how?
you didn't defeat him yet.
Cleverest
And I
thing
am.
existing.
Yeah, it's possible he can make you.
I would wish him
More than him, I cannot be.
that
He would be the cleverest.
I would
Seeing
wish
the
him that
to tell me the largest number.
So he will tell you.
I would ask him to tell me the largest.
He will tell you that it does not exist.
Yeah.
I would pick a mathematically incorrect equation and make him prove that it's right. Like he can grant me any wish, right?
Yeah.
My
So
wish is
what
like
you
suppose
ask
I
is you
take
will
like
tell. Please
yeah,
prove
1 plus
this.
1 equal to 4. It's incorrect, but my wish is that he has to prove it.
hello.
Yeah.
Well, I don't think he can do it.
What if he takes us to another
Yeah.
multiverse where 1 plus 1 is actually 4? Like, just a
Our
notation.
definition
Right?
of fun is like just one.
Our definition of
substance.
1 is 1, but what if?
Yeah, right. He can create a universe where actually two objects, when you bring together, they pop up into four. They kind of magically become
Yeah, that
four.
is already there, but like interference of waves and all, if you consider, then that is different. But like literally 1 and 1.
No,
Maybe
it's your perception of what is one and one. Right? Okay. Basically, you're trying to give him impossible tasks, but he's much smarter than you. Much smarter.
Okay.
You even don't have any idea what he might do. So I
I
want a sure shot way to beat him.
would ask him to abolish the greatest power of. Hello.
Yeah.
Yeah, I would ask him to abolish whoever person has the greatest on this earth. So basically, I am asking him to abolish God.
Kill himself or something, you're saying?
Sorry, what?
No, you ask him to kill himself. That's what you said.
Yeah, if he is saying that he is the God, then I would say that give up his powers. And if he's not claiming himself to be God, then I'm saying that take away the powers of the most powerful person in this earth.
Well, what if he's not the most powerful? There are other beings, his friends who are
Then
powerful than.
take
Hello,
powers of every power.
Yeah.
I will ask him to not grant me the wish, and if he grants that, he has already contradicted himself.
Yeah.
Yeah, that's the answer we are looking for.
Yeah,
Exactly.
exactly.
So the answer is this: do not fulfill my wish. So if he does fulfill the wish, then he is not fulfilling my wish by fulfilling my wish. So if he really does not fulfill my wish, then he is by not doing it, because that's what I asked. So it throws him into a dilemma, into a loop. He doesn't know anything. He doesn't know what to do. He agrees that okay, I can't do some things. It's a simple spell, but powerful one. As Dr. Strange said. Right. So this is clear, right? Okay. So Arnav will talk about this. So another similar puzzle.
Yeah, so yeah, I hope I'm audible. So basically Vikram and Vetal. Yeah, so basically Vetal always he gives some kind of riddle to Vikramaditya and asks him to solve him. So there are some three conditions. First, he cannot make any utter rubbish statement, otherwise he'll be killed. If the statement is false, then his head will explode and Vetal will be set free. And if the statement is true, then Beta either goes back to tree or grants prosperity to his kingdom. So basically, my question is, can you force Betal to grant prosperity to that kingdom? So it's one more logical puzzle. So try to come up with the answer. I hope the statement is clear. You can have a look at this slide too.
Yes, the question is clear, right, people?
So I will ask him not to go back to the tree.
So it's not asking, you have to make a statement.
Means don't go back to the tree.
No, that's not a that's not a yes or no statement. Yeah, okay. So you're ordering him. You have to make a statement of what he will do or something like that, and if he will decide what to do, if it is true or not.
Okay.
He won't go to the tree.
Exactly. Yes. So yeah, Arnab. So
yeah. You proceed to the next slide. That's the correct answer.
You will not go back. So why does this work? Why does this force the Betal to give prosperity to the kingdom? Can someone explain?
Yeah. Who told the answer? He can explain.
Okay. So if this statement is false, then my head was going to explode. But then his only option is to grant me prosperity to his kingdom. And I mean, again, we have this question is similar to the first question. We are using just a loop, a contradicting statements. He can't do one without giving the other. Basically.
Right, but your explanation is not what you said.
May I explain?
Yeah.
So if Vetal goes back to the tree, so then Vikramaditya's statement "he will not go back" should be false. So basically, he cannot go back, because if he goes back, that is the condition under the first statement to be true. But his going back makes the statement to be false. Am I clear?
Yeah. I think you should start with assuming whether the statement is true or false, not the action of the question. First assume it's true. If it's true,
you will not go back. If it is true,
if it is true, then either he has to go back or grant him wish. But because it's true, he cannot go back. So the only option left is granting prosperity. But if other case, then if it is false, then he will just die and then he will be set free. Which is a subcase of him not going back. He'll be set free. So it's actually true what he told. So it cannot be false. Right. So yeah, Arnab will continue.
Yeah, I'll share my screen once. Yeah, just 1 second. Yeah. So I hope I'm audible. So yeah. So last time we asked these questions like, are there as many natural numbers as there integers? So by this what we meant was whether there is a one-to-one mapping between natural numbers and integers, something of this type, one-to-one mapping, which exists between integers and natural numbers, 1, 0, 2, 1, 3 minus 1, 4, 2, 5 minus 2, and so on. It will continue. So if such a mapping exists, so we say that the both set of infinities are of same size. So it's sort of an definition or sort of intuition, you can say. If you can establish one-to-one mapping, then it's sort of same size. So So the next question which we'll ask is whether there exists like one-to-one mapping between natural numbers and rational numbers. So I'll ask the audience. So what do you think? Like, can you establish a one-to-one mapping, like how
Yes.
we are doing it here?
No, we
So
can't.
can you do it for the case of natural numbers and rational numbers?
Yes.
No.
No, we can't.
So first,
No, we can't.
why no? Why no? People answer why.
Yes.
Yeah.
Yes, we
Because
can.
No. Yes, no. As afterwards,
Okay,
but
so it's
why no?
about the orders of infinity, right? So these natural numbers, integers, and all come under one category of infinity, whereas these rational and real numbers and all come under another. Like that,
No,
that
no.
infinity is bigger than this infinity.
No, yeah. If you feel it's bigger, then tell me why it's bigger. Like,
between two natural numbers, there are infinite rational numbers.
Yeah.
We can say that between two natural numbers, maybe we can,
no. Okay, so don't like that argument is not correct, because what I asked for is whether you can establish one-to-one mapping. Okay, the mapping can continue forever. So
Yeah.
just tell me whether there's a one-to-one mapping between natural numbers and rational numbers.
Yeah, we can't do one-to-one mapping because for doing it in integers and natural numbers, these numbers are visible numbers, means we can jot it down for mapping. But rational numbers are not like these numbers. We know they exist, but we don't know their values.
So you're telling you can list all the naturals and integers, but you cannot list all the rationals. That's what you're saying?
Yeah.
Can you tell the method?
Actually, okay,
What
it's not
about
clear
the
why you
fact-
cannot list.
What about
Maybe
the
someone
fact
else can come up with a list.
I can list.
Yes, could the list be like this? 1 by 1, then 1 by 2, and 2 by 2 is again 1. Then we go 1 by 3, 2 by 3. Could we continue like this?
Yeah, you're almost near.
Yeah,
We
this
can
could
continue
result in a
one by
list of
one,
all
one
rational
by
But
numbers.
what
one
about the
by
fact that 4 by 2
1
is
by
same
4.
as 8 by 4, like that? Those also like they'll stop the mapping.
4 by 8 is same as 1 by 2, right?
Yeah, but they'll stop the mapping, right?
No. You're not going to map to that. So what he told is almost nearby actually to what actual thing is.
We can do 1 by 1, 1 by 2, 1 by 3, 1 by 4 till 1 by n.
No, what is that till? What do you mean by till? You don't, you will
Yeah.
be in a loop, right? You will just be doing this. You won't cover other numbers.
Yeah.
You'll be
Yes,
stuck in 1 by
then
x.
in the next, then in the next row we will do 2 by 1, 2 by 2, 2 by 3.
Then what about 1 by, if 1 by n, suppose n is 100, then what about 1 by 101, 1 by 102 and up to so on? How will you cover those?
A natural number and immediate
I will
rational
map.
number. If we map those, there would be left rational numbers in them.
No, what was your mapping? Can you tell again?
A natural number and immediate rational number.
What do you mean by immediate rational?
There's nothing like immediate rational number, I guess. There can be
Arbitrary
like
close.
arbitrary close rational numbers.
We can go in a zigzag manner, that 0 to 1 by 1 to 2 by 1 to 1 by 2 to then 1 by, then 2 by 3, then 3 by 3, then again 4 by, then again
3 by 3 you shouldn't be doing because already you covered it 1 by 1.
we will skip that and then we will go in a zigzag manner.
Yeah. So okay. So the question. Okay. So before that. Okay. So let me give one more hint. Can you do a bijection between natural number set and the natural number pair square? Means a comma b, that coordinate set, 2D points whose coordinates are integers, sort of integers and natural numbers. So can you do mapping between these both? If you can do this, then you can get an idea for natural numbers and rational numbers. So you have 1, 2, 3, 4 up to so on, and then you have those pairs 1, 2, 10, 12. So can you show a bijection between these two sets?
I don't think we can do it.
If you don't think, then can you tell the reason? Because for anything you claim in maths, you need to give some kind of reason.
So assuming we do one-to-one mapping is like you take a number 1, 2, 3 and all, and then you map it with some 2D point, okay? And assuming that these are the points on the x-axis, like the ones you map like 1, 2, 3, and then the points on 2D plane are like in some bracket x comma y, like then you map those points to the points on x-axis. But then what about the points on x-axis itself? They are also part of 2D plane, right?
No, I didn't get your exact argument. Like,
Can I tell the answer? Okay.
Yeah, move to the next slide, I guess.
No, I had okay.
Look at this.
Just look at this mapping. You cover in this fashion. And you continue in zigzag fashion.
Like people understand why it's a proper mapping. Like every number will be mapped to every x comma y, and every x comma y will be covered. Nothing will be missed.
It will be just covering each and every point as it gradually goes on.
We are creating a list of all the pairs.
Yeah, so it starts like this, then you go like this, and then you continue like this up to here, and then you keep on going zigzag in this fashion, and you get the answer. These are this mapping.
In fact, this is called lexicographic order, basically, of all pairs. I mean, you'll study it when you see about strings, or it will be more, but this is very clear. You can understand.
Yeah. So let's give for rational numbers too. So for rational numbers, you continue like this, but you start skipping. Like since you already covered one by one, you just skip and then see this number will be mapped to 1. This number will be mapped to 2, then 3, then 4. You skip this, then it will be 5, then 6, 7, 8, 9, 10, and you continue in this fashion. And this is sort of the table, like a list of rational numbers. You can see, like 1 by 1, 2 up to so on, and 2 by 1, and then all the possible rational numbers are being covered. So this sort of a list of rational numbers. Intuitively, you can think of this fashion, and then you can start mapping it like this, and you go on. So this for
anyone has any doubt from your previous thinking and how this is? I mean, is it clear why you can list?
I can't mean by pairing.
No. What? Can you repeat your question?
I can't able to understand what is meant by pairing.
It's not pairing. It's like this. Like so you have a set of natural numbers and you have to like do a mapping. I know, at least I hope you know what mapping is. Like bijective mapping, one-to-one mapping actually. That is basic J stuff. So like you take 1 and you map it with 0, 2 and 1, 3 minus 1. So this is one-to-one mapping. So what we are asking is, can you do a mapping between natural numbers and the set of rational numbers? So that's what we are asking from you. So if you continue mapping natural numbers to rational numbers along this order, then you will cover all rational numbers using the set of natural numbers. So this is a one-to-one mapping between the natural numbers and rational numbers. Is it clear, or still you are confused somewhere?
Clear.
I mean, basically the point is to show that both the infinities are same. As someone told that rationals are bigger, but we just proved that they are not bigger, they're as big as the naturals.
Yeah, perceiving it will be quite difficult for you guys, but when you do a one-to-one mapping between two sets, then it's sort of a notion, you can say, that both sets are considered to be equal because they are able to show a one-to-one mapping between the two sets. Yeah. So I'll proceed to the next slide. Okay. So the next question is, can we have a one-to-one mapping between real numbers and natural numbers?
No,
So
we cannot list the irrational numbers.
like, okay, the similar, okay, so you got to give some kind of solid argument. Okay.
Yeah, previously
Not-
someone told you cannot list rationals also, but clearly we saw a way. But yeah, so your argument is not the line of argument is not correct. Simply saying
Yeah.
that
Yeah.
you cannot map is not a proof.
Yeah. You like, if you believe that your statement is true, then you have to give a proof of why your statement is correct.
Irrational numbers are not defined. For example, we do not know the exact value of pi.
Yeah, but suppose I will say pi is my first number, even though I don't know its value. I'll say it is my first number. I'll say my second number is e. My third number is log 10 or something. I mean, why is it not possible to list all the reals?
Yeah.
Maybe I'll create a black box. If I ask for the nth number, it will give me the nth real number. And if I give the real number on this side, then it will give me its ID. Which number is it in the list? Will such a box exist? Black box.
Okay, so I think we can map it. I don't know how, but just in the nature, as we have seen for mapping natural numbers and integers, we were on a number line. For natural numbers and rational numbers, we use a 2D plane. So maybe we can use a 3D plane for this mapping by seeing the symmetricity in the nature.
No, someone else. So basically, we're asking you to. So in a classroom, there are all real numbers. You have to give them roll numbers. That is the question basically. Give them roll number so that if I ask, okay, roll number 100, stand up, some real should
I can
come
try. We can go like if we if we map like 1 to 1, and then 2 to 1.1, and then 3 to 1.11, and then 4 to 1.1111. If we go on like this, so if we
where
start
is 2 then? Where is 2?
Where is 2? Where is 3?
That is what if
I will
we
try
map
to
1
show
with 0.
that.
So, just a second. If we map 1 with 0, and then 2 with 0.1, and then 3 with 0.01, and then 4 with 0.001, we are going back. We included 0 and then 0.1, and then we are going back. Like we will stay in the interval from 0 to 0.1 on the real for the real numbers, whereas all the natural numbers will be finished in can be mapped.
That's pure mapping. The same, we can do the same thing for rational numbers and natural numbers too.
Got it.
Yeah.
Yeah, you can
so
give a
that's
mapping so that it's bad. It's not covering everyone. That doesn't prove anything.
I would say that if we write a number, then if we write the decimal expansion of any number, then the probability of writing a decimal expansion which has a pattern is less than that of writing a decimal expansion which does not have a pattern, means writing absurd or arbitrary numbers. So I can show that irrational numbers are more than rational numbers, so they are more than natural numbers.
No, even rationals, if I pinpoint a number, if I give you all the rationals, if you randomly select a number, the probability that it's natural is 0, but the probability that it is rational is 1. That doesn't again prove anything. Density doesn't prove cardinality.
Yeah, basically when you are dealing with infinite sets, don't think as sizes, like think as one-to-one mapping. Size doesn't have any sense when you are dealing with infinite sets actually. So try to establish whether there is one-to-one mapping between the two sets or not.
Yeah, rationals are very dense, but it turned out that you can actually list them.
Hello.
Yeah.
I can list a irrational number like 1.1, 2, 3, 4, 5, 6, and so on. This goes up to infinity. Okay, and I will match this number with 1. And for natural number 2, I will create a new number like 1.23456, and this goes up to infinity. Similarly, for 3, I will write 1.3 and so on up to infinity. So clearly, I will have more irrationals than natural numbers.
No,
And third,
that's again I told don't. Okay, so that's the problem of your mapping actually. That's not a proof that there are more irrational numbers than natural numbers. Okay. Yeah, that's a problem of your mapping actually.
Okay, can we
what
do
kind of
mapping in this way?
problem?
Till someone
Can
was
we,
speaking.
yeah. Can we do mapping in this way that we'll first divide real numbers into rational and irrational? For rational numbers, we'll use this same mapping on xy plane. And for xz plane, we'll use circles for mapping, like we use zigzag here. That will cover all those numbers in between them, most probably.
No, how are you moving on the circle? Like, I don't understand what you're thinking.
Like we'll take the axis as fixed axis of those like this for mapping 1, 2, 3, these, and then we'll just draw circles. I don't know how, I can't visualize it right now, but still, is there a way? Can that be a way? I mean,
No.
Well, okay, the thing is, whatever you
Make
try,
one by one
whatever you try,
process.
yeah, you can never cover all the reals. And that's a fact, and we'll
Let's
show you.
prove it. So this is not possible. Okay. So suppose we'll prove it by contradiction. Okay. So suppose someone came up with a list. Okay. So this is just example. You can do it for any kind of list. Okay. Suppose there is a list covering all real numbers, which is of this type. Okay. And it continues. So what we do, the idea is that we create another real number which is not in the list actually, which will show that this is not a list which covers all the integers, all the real numbers, and hence we have a contradiction. So let's show how do we construct such a list, such a real number. Okay. So what we do, okay. So the left of decimal will keep it as 0 itself, not an issue. So for the first number in the list, we'll look at the first decimal place and we'll choose something which is different from this decimal place actually, like 2. Okay. Then we'll look at the second decimal place of second number and we'll choose here something which is different from 3, which is 4. Like we can choose any number except 3. Similarly, for third decimal place, we'll choose for third digit. We'll look at the third decimal place and we'll choose something different. Similarly, for fourth number, we'll look at the fourth decimal place and choose something different. For fifth, we'll look at fifth decimal place and we'll choose something different. For sixth, similarly, we'll look at the sixth place and we'll choose something different. And we'll continue like this. And this number won't be in the list. Okay. Suppose this number was in the list and say it was at the ith position. But by our way of choosing this number's ith position and the ith number in the list should differ. Like the decimal place at ith position should differ from the number at the ith decimal place. Like suppose I was 3. Like this number is at the third decimal place, but third decimal place of this number and third decimal place of this number is different. So it means that this number cannot be part of this list. So it means that this list does not cover each and every real number. So it means that our initial assumption is wrong. So hence proof by contradiction that the list of all, like we cannot like sort of list the real numbers. We cannot do a one-to-one mapping between natural numbers and real numbers. So I hope the proof is clear. If someone has any doubt, they can ask.
Like it's clear, right? You look at the diagonal and change every bit. So basically the new number cannot be in any position because there is a mismatch at some point, some digit. So that way you cannot list all the reals and that's it.
Yeah, someone was saying something.
Yeah, I have a doubt, but different from what you are teaching. Can I ask?
Yeah, fine.
Yes.
Does the number of numbers between 1 and 2 are equal to the number of numbers between 2 and 3?
Yes. Yes.
If this is true, then the graph of x square is not continuous. I can prove.
What do you mean x square is not continuous?
The graph of x square is not continuous graph.
Why?
If what I said earlier is true, then graph will not continuous.
How?
Yeah, why? What's your argument?
Let's suppose the number between 1 and 2 and 2 and 3 are equal.
Okay.
And if we look at the graph, y is equal to x square. At x equal to 1, y equal to 1. And x equal to 2, y equals 4.
Yeah.
But in x axis, a number between 1 and 2, let's suppose t, and in y, number between 1 and 4 is 3t. Then how we can map the all x to y?
Yeah, you see again previously you look at the number of naturals and number of even numbers. Do you say it's half of this?
Repeat again, please.
Look at the natural numbers and look at even numbers. Like naturals are 1, 2, 3, 4 up to so on. Even are 2, 4, 6 up to so on. So basically, you're thinking this is half the number of naturals, right? That's what you're thinking. But that's not true. They are equal. That's the whole point. That's how infinities behave. Like as you said, t and 3t. T is not finite here. T is infinite. So they can still be the same thing.
But we can say number between 1 and 4 is 3 times the number between 1 and 2.
No, that's not right.
But you said it earlier.
No, we want a 1-to-1 mapping actually.
So again, it's not equal. It's equivalence. Those two infinities. So when you said number of numbers, it's not a number, right? It's an infinity. We're trying to compare infinities. So instead of x square, I'll tell x cube. Then it becomes 7 times, as you told. Then what is the relation between those two? And I will get another graph. Then we'll see that the other one is 7 times of this one. How can two things be 7 times of each other? Like I can choose another graph, and get all weird values. None of them are true. They're all equivalent.
Then it's mean only y is equal to x and constant function are continuous.
No. I mean, what do you mean by continuous? Why are you arguing that way? I mean, how are you comparing? Yeah. Tell.
I just said what I had to say.
Yeah. Okay. I mean, it's hard to grasp these things, but over time you will get it. I know it's not intuitive. It kind of breaks your head that okay, what? How can even numbers and natural be same? Clearly, one is contained in another, and it's half of one another. But yeah, that's what is your intuition. But it turned out it's not that way. Okay. I mean, anyone will be confused with this stuff initially, but that's why it's interesting. Okay, now continue.
Okay, so okay, so I should reveal it, but okay. Okay, so the question was actually that whether the interval -1 to 1, does it have same number of like again what Madhu was trying to mean is equals. Like, does there exist a 1-to-1 mapping between the rational numbers, not rational numbers, the real numbers in the interval 1 to 1 and all the real numbers? So can you create such an equivalence actually? By equivalence, I mean again 1-to-1 mapping. Like you take any real number from -1 to 1 and you map it to a real number like from -infinity to +infinity. And it turns out to be yes. Try to think on your own. This diagram is given as a hint. I hope you should get it by seeing this diagram. Why it will be true actually.
Yeah, I think
So-
I actually want some of you to give the function actually. You can you know the function actually.
Yeah.
Given a number x between -1 to 1, how to get a real and how to get the reverse. With your JE knowledge, you can do that.
Yeah.
Plus 1 by x. Sorry, x plus 1 whole by x. Sorry, what am I saying? X by x plus 1, sorry.
X by x plus 1, no, it's a no, it won't cover all reals. No?
This should, I guess, use trigonometry, I guess.
Yes.
This is circular, this is an arc basically. So try to use your trigonometry. Like which function used to go from -infinity to +infinity? Just try to recall that.
We can do tan inverse x of
Yeah.
Yeah. So given an angle theta, map it to tan pi by 2x. That will give you the x value. Right. So x from 1 to -1 will map to -infinity to infinity. So the number of numbers in -1 to 1 is same as, again when I say same, it's not equal to, it's something else because they're infinities. So there is a mapping, but so basically all these numbers are simply mapped in this interval. This interval has in fact more numbers than naturals, this small interval. That's amazing, right? This -1 to 1 has more points than all the naturals.
Yeah, sort of you can say like we are trying to establish an equivalence. Otherwise, it's counterintuitive, right? Like -1 to 1 is part of that whole real number, like whole this x-axis. Then how can it be equivalent? So it's like equivalent mapping actually. There is a mapping for each point to another point. So that's the power of infinity actually. So if it was just a length, then it like okay. So that also you have to think, but it's sort of equivalency, like how we proved it before. Like there has to be a 1-to-1 mapping, like someone told tan pi by 2x. So it's a 1-to-1 mapping. So it's of that type. This one will leave it to you. So this is a square box of 1 unit, and this is an interval of 1 unit. So does there exist a 1-to-1 mapping between this line and this box, including the region inside? So does there exist a mapping? The answer is yes. You can take a screenshot or we'll share the slides. Try to come up with a function which maps say a point here to a point here. So try to come up with such a function.
And the function need not be analytical like previously tan pi by 2x. You can give a way to map.
Yeah, you can create your own function and it should be properly defined and it should be 1-to-1 mapping. That's the only condition which we need.
Is it just the perimeter?
Is the length of the
or all the points inside the box are considered?
Yeah, all the points inside the box are considered, including the boundary, I guess.
Yeah, should work.
Is the length of the line and the length of the side of the box same?
Yeah, same. Yeah, same.
Yeah, both are unit, say.
Both are unit.
Matter actually by what I have told, because you can scale things and still it will be same.
Yeah.
So anyway, assume both are unit.
Yeah.
Yeah, now move fast.
Yeah.
So I can...
Yeah, you can take over now.
Yeah, fine. So
you can take over. You can share your.
Go back.
Okay, 1 second.
Fine, okay, then I'll share.
Okay.
So you can see my slides.
Yeah. Just do the screen. Yes. Slideshow once.
No, can you see my screen or did I not share?
No, we can see your screen, but not the slideshow. Like we can see the slides, but it's not in the.
Okay.
Yeah. Till
So
now it came. Yeah.
I'll summarize. We went through two nice paradoxes and how paradoxes can prove stuff, and we proved that reals can't be mapped to naturals, and we proved that rationals and integers can be mapped, and there's a puzzle. So again, one more question: is there any infinity bigger than the reals? So we proved that naturals, integers, rationals are one infinity, and reals is another infinity which is bigger than this. But are there much more bigger ones? And it turns out, yes, there is a whole hierarchy of infinities, and there is a big question called the continuum hypothesis. So we'll look at it later because we can't do it now. So now the final question. Everything is fine now these days. Machine learning is coming, artificial intelligence coming. Maybe one day, could it be possible that machines can do everything? Could there exist an ultimate machine M that can answer all your questions? Can someone share your opinion? What do you think?
It cannot be true for a mathematics question because there exists no particular universal answer for a question.
No, there in mathematics there does, right? That's why mathematics is cool. We have definitive answers and we just want a proof. You make a statement, either it's true or false, or it's just yeah.
Machine can't do anything. Machine can't do everything because machine can't understand infinity. What is infinity?
Maybe it can. Maybe there is a machine. See, if we can think about something, if we can perceive something, maybe we'll replicate a robot and kind of transfer our mechanism, our thinking, and it's more intelligent than us. And it can perceive all math, it can solve puzzles, it can do everything, it can answer hard questions. Maybe. Why not?
But till now, machine can't understand infinity because
yes, till now. The question is whether at any point can it happen that there is an ultimate machine that can answer all your questions?
No, I think.
Okay. So can we use the same concept as we used in the God problem here?
Yeah, maybe we can fool them also.
Yeah, just replacing God by this machine. It will always we have
but
contradicting.
the machine doesn't say I'm going to grant you wishes.
Yeah, I know, but I'll just take him into that loop where it can't answer and answer at the same time. Means give me output and not give me output.
Yeah, so yeah, more or less it turns out this kind of self-referencing paradoxical stuff will disprove.
Yeah, exactly. Yeah.
Right. Okay. I mean, it's very important. This self-referencing is very important. But I think something is really intelligent when it can perceive itself. Like us, we are conscious, we are aware. We can think about ourselves. We can think about thinking. It's called metacognition. So when a machine is able to do that, I think it's really intelligent. But even though there are things it cannot do, we'll give a proof. So yeah. So we'll go through a short movie kind of. It only has screenshots, but there is a link that we'll post. You can see. So prove that computers can't do everything. Act 1. A few things computers do really well. So we'll just go through few things that computers are very good at. So look at machine A. How does it work? On a piece of paper, you write down an arithmetic question and put it, like it'll take it and scan it and then process and then output the answer on a piece of paper, right? So suppose there exists such a machine, and there does exist such a machines, right? Like you can type whatever you want in your computer and it will answer. Okay, so that seems okay. And there is another machine C that plays checkers very well. So you input a state of checker, like checker or chess. It will scan, process, and output its move, what move it's going to make. Okay. So this way, maybe there exists the ultimate checker playing machine. That also could happen, right? Now a more challenging task. So Act 2, this is called the halting problem. So what might happen if we give the arithmetic machine the checker puzzle? Like, it's not designed to solve checker puzzle, right? So we're trying to look at general intelligence. If a machine can only do calculations, it's called calculator. If a machine can only play chess, then it's a chess bot. But to be intelligent, you should be able to, do everything. Like, it should be able to perform multiple things. Like, we can do many things, right? We can play, we can solve puzzles, we can do math. So A might actually get stuck. And if you give arithmetic question to C, it might get stuck. Right. But so you basically gave a checker puzzle and observed that it's not outputting anything. It's just it's just giving a sound, processing sound, and it's not giving any out.
Yeah, so like intuitively you can think like if you guys have started coding in lab, sometimes you might have done some coding mistake, and the program is not stopping. It's just keeping on running, like infinite loop of that type actually. In case if you have encountered those stuff, like it's not stopping, it's not giving output. The code is just running continuously without stopping. So it's something of this type actually.
Yeah. And what will you do? You'll go into the code and see, okay, here I did a mistake. That's why it's getting a while loop, or it's stuck. So first of all, how do you know? Maybe it will be nice to design a software that will say whether it's stuck in a loop or it's processing, right? Like you design a machine, you give an input, it's not giving any output. Maybe processing, maybe it will, or it will not. So you don't know whether it halt or it won't, or it doesn't. Like, it's a very tricky question, right? So for example, imagine you are outside a room, and maybe there is a guy inside a room or not, you don't know, but you knock and ask, is anybody there? And no one answered. Maybe he is, but he's sleeping. Maybe you should try more times. Or nobody's there in the room. In which case, you'll just keep knocking. You'll never know whether there is a person but he's sleeping, or there is no one. So this dilemma is similar to that. So it would be nice if we kind of look at if there is a machine H for which we can give the blueprint of A, like the mechanism of A, everything we describe, and give it to H and another input. So what I'm saying basically is, if there is a machine H that will take the description of another machine and some input, and it will simulate A, it will look at the code and decide whether it will halt or not, and it will tell you it won't get stuck. This is right because H knows that upon giving 3 plus 5 to A, it will give 8. So A won't get stuck. So it will output not stuck. Okay, let us assume such a machine exists, H. So this machine H we want, right? It's nice. Whether you look at a machine and it is stuck or not, you don't know. How do you know? You just take its description and the input you gave to it, and you give this machine, and it will tell you whether it will get stuck or not. If it gets stuck, then you will stop the machine, right? Why waste your power? So that's the point. If you give the checker input to A, then you know that A will get stuck. So H will tell you that it will get stuck, basically, right? So H saved us from running A. And again, if we give C and 3 plus 5, we know that C got stuck and H will tell you that, right? So that is H, and we'll prove that H cannot exist. So this is a halting theorem. So first of all, before proving, we'll look at some basic machines. So P is a photocopy printer. So you give one output, one input, then it will give, it will just produce one more copy of the input and the initial original copy. It's just a Xerox machine. So this guy is so interesting. Like if you give the input as not stuck, it will get stuck in a loop. It won't do anything. Okay. So if its input is stuck, then it will just output a smiley face. That's it. So that's simple, right? So now what we'll do? So we'll construct this machine. Like we'll put a printer and we'll connect it to our H machine, and then we'll connect it to our N machine. So we'll see what will happen. We'll observe that something interesting will happen, right? And we'll enclose this entire machine in a box, and we'll call it X. X basically has an input and output. This is the internal working of it. So which we don't care for now. Just look at this new machine X. So X has this description, right? We know what X is. A printer, a H machine, and the negator N. So there's a description of it, X. So what will happen if I feed the description of X to X? Can anyone guess? I mean, is everyone following until now? Is it clear what machines are, what they're inputting?
Yeah, so like so intuitively you can think in this fashion. What we are trying to do, we are trying to see if you want to understand in terms of coding perspective. If some of you have started coding in labs and all, so what we want to do, we want to write a code which will see another code and its input and tell whether the code will get stuck in some loop or not. So that's what we are trying to show, that such a code we cannot write actually. So it's intuitively that. So just using this machine kind of model, we are just explaining the same thing actually.
Yeah, so people, you tell, like, is it clear what's happening? What you understand what is a description and what is happening till now, right? How we constructed X.
If we get an output of not getting stuck, then eventually it will get stuck. And if we get an output probably it gets stuck at the final juncture.
Yeah, so look at this. So basically you're giving the description of X to X. So we'll look at inside what is happening. So the photocopy guy will just produce 2 copies and give it to H. Okay. So what will H think now? So H is given a description of X and another copy of X. So H will start thinking, okay, so it basically have to solve this problem. What will happen when I give X to X? Right, that is what H does. And suppose it will guess that, okay, maybe it will terminate. It will just output the smiley. Then what will H do? It will just give not stuck. Then what will my negate to? Previously, I have seen that this N machine, when we give not stuck, it will get stuck. So when H gives not stuck, then this guy will get stuck. So what H guessed is wrong. Upon giving X, machine X got stuck. Like assuming that H calculates that it will not get stuck, and it got stuck. So suppose H will now guess that X will get stuck upon giving input X. Now what it will output? It will output stuck. My negator, what it will do? Upon input stuck, it will just output smiley. So X did not get stuck upon input X. So H was wrong in both cases. Said H should not exist. Such a machine. Yeah.
I think that H would not give any response because then it would fall into an infinite loop. H should
Yeah,
in fact get stuck.
H should get stuck. So that also contradicts its property, right? We assume that. What?
Can you mute yourself?
Anyway, you guys have some questions? What happened? You got confused.
Yeah, I was telling that I think that H will just go into an infinite loop, no? Like according to
Yeah,
the
that would be
inputs we have
fine.
given.
But the point is, where we assume that H is a machine that will always give the right input, right output. Or like you give the description of a machine and an input, it will study what will happen if you give that input to that machine, and it will just tell. It won't get stuck in a loop. We assume that.
Okay.
Yeah.
But if we don't add the negator, then
If we show a contradiction in one case, then that should be enough.
yes, that's it.
Yeah.
Okay. Thank you.
The point is negator is doing the. I mean, it's tricking the. That is where the real job is going on. H will always be false. Whatever H will predict, that prediction will go wrong. It's something like that.
Yeah, and if someone is getting confused regarding the description part, like what do you mean by description? Just think in terms of code. So in previous lab, in future labs, you'll see that you can give a code as an input to another code. That's possible. Okay. So the code can, like, basically machine, it's running some code, suppose. So basically code is the description of the machine. So you are giving the code only as the input to another code and asking that other code to check whether this code will get stuck in some infinite loop or not. So this is what we are asking, and we show that this type of code we cannot write. So that
This halting theorem, this proof that machines cannot do everything is done by Alan Turing. Is called father of theoretical computer science. There is a movie. What is the name of the movie?
Imitation Game. Imitation.
Yes. So the Imitation Game. It's about Alan Turing. You should watch that movie. It's brilliant. So this guy created the whole notion of computation. The theoretical part of this computer science. Yeah, breaking the enigma. Okay. So so we proved that machines cannot possibly do everything. Well, can a god can answer a question? So if not a machine, if not the description and stuff, maybe it's a person. So maybe there is a god who will answer all your questions. Can such a god exist? Like you ask him an yes or no question, he will answer yes or no. That's it, and it is right. It is the eternal truth. If not, machines can God do everything, or does not? You have to prove it. Anyone has any ideas? You should already have a clue that answer is no. There cannot exist such a God who can answer correctly to every question. So anyone, any ideas?
Can we give that dilemma that we used to prove in the first case? That the missing case.
So what exactly the statement that you'll ask? So I am the God. Okay, assume I am the God. Now you can query me. I'll try to answer. I might not, but yeah, we will try to simulate the question here. So I am the God. I am here to answer all your questions. Please answer. Ask me any question you want. It should be yes or no. You cannot say go and die. Okay. Anyone?
Is your next answer going
Can you answer this question with no?
Yeah. Is it visible in my slide or what? Yeah.
No.
Right.
It's
so
not visible.
he asked the following question. Will you answer no to this question? So the question is this. Will you answer no after this statement? Something like that. Will you answer no to this question? If I say yes, that's wrong, right? I said I agreed that I will answer no, but I answered yes. But if I say no, I'm actually doing it. Why did I say no? So boom, paradox. I cannot say yes or no to this question. So basically all of these are linked with what is called the liar's paradox. I am lying. If I say I am lying, if it is true, then it's false. If it is false, then it's true. So almost all of these are built on this self-reference. The statement is referring to itself. So actually, this is the crux of our machine proof. Kind of. All this, I mean, almost every chapter in this talk is kind of the puzzles and mapping with reals and integers, why it's not possible. All of these are linked with this. That's a paradox are very important in mathematics. Lot of impossibility theorems are done using this. So yeah, that's it. We have basically seen that there are many things that gods can't do, machines can't do, we can't do, right, with proof. Right. Yeah, that's it. You have any questions? You want to ask something else? You can ask.
Yeah, I am Sanil Upasni, and I did not